Hello everyone, now we have to discuss the next theorem, that is Norton's theorem. So, before starting this theorem, I would like to tell you something, that is, if you know the concept of Thevenin's theorem, this theorem concept is very easy. So, for example, if you consider the statement, any two terminal linear bilateral DC circuit can be replaced by an equivalent circuit consisting of a current source in parallel with a resistance. So, this is the statement for Norton's theorem, but in case of Thevenin's theorem, what is the statement? Any two terminal linear bilateral DC circuit can be replaced by an equivalent circuit consisting of a voltage source in series with a resistance. So, up to this point the statement is same, but there consisting of a voltage source in series with a resistance. So, lot of similarities between Thevenin's theorem and Norton's theorem. In that we have voltage, here we have current. In that voltage source is connected in series with Thevenin's resistance, here it is connected in parallel with the resistance. Okay. So, this is the first similarity of that Norton's theorem and Thevenin's theorem. At last, we have to compare Thevenin's Norton's. Okay. This is the statement for Norton's theorem. That is, what is the statement? Any two terminal linear bilateral DC circuit can be replaced by an equivalent circuit consisting of a current source which is connected in parallel with the resistance. The resistance is nothing but Norton's resistance. The name itself Norton's, no? That is why Norton's resistance. Here the current is what? Norton's current or short circuit current. Okay. With respect to one problem, I will explain the procedure. Okay. So, this is the problem. So, with respect to this problem, I will explain the procedure, that how to calculate corresponding branch current or power loss or whatever it may be by using Thevenin's theorem. So, this is the problem. So, from this calculate the current through 4 ohm branch by using Norton's theorem. So, he wants the current through this branch, only this branch through 4 ohm branch, means this is terminal 1, this is terminal 2. Okay. So, we have to calculate the current through this branch by using Norton's theorem. So, for this we have to write the step 1. This is step 1. So, remove load resistance RL, that is, for us this is the load resistance, no, that is 4 ohm branch, and short circuit the load terminals, then calculate short circuit current, that is ISC or Norton's current. The current is nothing but short circuit current or Norton's current. In case of Thevenin's theorem, remove load resistance RL and open circuit the load terminals and calculate the open circuit voltage or Thevenin's voltage. Here short circuit the load terminals and calculate the current, that current is nothing but short circuit current or Norton's current. So, lot of similarities between this Thevenin's Norton's theorem. There we have voltage, here we have current, there we have open circuited, here we have short circuited, there we have to calculate open circuit voltage, here we have to calculate short circuit current. That voltage is nothing but Thevenin's voltage, here it is Norton's current. So, like this we have to compare Thevenin's theorem and Norton's theorem. Okay. So, with respect to this step 1, we have to modify this circuit. Okay. Remove this load resistance and short circuit these two terminals and calculate the short circuit current, that is nothing but Norton's current. With respect to this step 1, we have successfully remove that load branch and short circuit these two terminals and calculate the current, that is nothing but ISC or IN. That current is nothing but short circuit current or Norton's current. Okay. So, to calculate the current through this branch, I am using nodal analysis. Okay. Here we have two nodes. This is one node, node A, and this is another node, node B. So, at node A, Okay. It is V A minus 10 by 2 plus V A by 3 plus V A minus V B by 1, which is equals to 0. So, this is the KCL equation at this node A. So, from this 3 V A minus 30 plus 2 V A plus 6 V A minus 6 V B is equals to 0. So, 3 plus 5, that is 11 V A minus 6 V B is equals to 30. This is 1. So, like this at node B, from here this is leaving, but by default the current is entering towards the node, here leaving, because we have to calculate this current ISC. So, that is entering current is equals to I 5 and V B minus V A by 1 plus V B minus 0 by 2. Here we have one branch resistance, that is V B by 2. From this 2 V B minus 2 V A plus V B is equals to 10. So, minus 2 V A plus 3 V B is equals to 10. So, this is equation 1 with respect to node A, this is equation 2 with respect to node B. So, by solving those two equations we will get V A and V B. From 1 and 2, 11 V A minus 6 V B, which is equals to 30, and we have to multiply the second equation with 2, that is minus 4 V A plus 6 V B, which is equals to what? 20. So, finally, we have 7 V A, which is equals to 50. V A is equals to 50 by 7 volts. This is voltage at that node A. Like this, what is the value of from 2 minus 2 into 50 by 7 plus 3 V B is equals to 10. So, 3 V B is equals to 10 plus 100 by 7, that is 170 by 7. V B is equals to what? Approximately 170 by 21. 170 by 21. So, this is V B. Okay. So, what is the value of current? That is ISC is nothing but V B by 2. This is the current we want to calculate, ISC, that is V B by 2. So, V B is nothing but, therefore, ISC or IN, which is equals to what? V B by 2, which is equals to 170 by 42. 170 by 42, approximately we will get 4, approximately we will get 4 amps. Okay. Approximately we will get ISC as 4 amps, that is 42 into 4, approximately 168. Here we have 170. So, 4.0, like that we will get. Okay. This is the value of short circuit current through that branch. So, what is the step 1? We have to remove that low resistance and short circuit those two terminals and calculate the short circuit current. Okay. Next, we will discuss step 2. So, in the case of Thevenin's theorem, what is step 2? Deactivate all constant sources with their internal resistances and calculate the equivalent resistance. The same step 2 can be applicable here. There is no change in the value of resistance. Here we have the resistance, that is R n, because Norton's resistance, the name itself Norton's, no, but there we have Thevenin's resistance. Those two values are same. Okay. Remove load terminals and deactivate all sources with their internal resistances and calculate the equivalent resistance. That resistance is nothing but Norton's resistance. Okay. We have to remove this part total. We have to deactivate these load terminals. Okay. Then the circuit becomes plus minus. Sorry, this is short circuited, no? Short circuited. We have resistance branch here. Again one resistance again we have one resistance. This is open circuited because this is current source and we have a one branch. So, remove load terminals and replace the constant sources with their internal resistances. So, voltage source by short circuited, current source by open circuited. This is 2 ohms, this is 3 ohms, this is 1 ohm and this is 2. So, with respect to these two terminals, that is R and we have to calculate. So, by looking between these two terminals means what this is like this. These two are in series, these two are in parallel. So, by looking between these two terminals, first we have to reduce the circuit from this side to this side. So, first we have to solve these two are in parallel, then this combination is connected in series with this circuit. Okay? Then the circuit becomes Rn. This is what? 2 into 3 by 2 plus 3, which is equals to 2 into 3 by 2 plus 3, which is equals to 6 by 5 ohms. This is 1 and this is 2, 1 and 2. Now, it is Rn, that is Norton's resistance. This is 3 ohms and this is 6 by ohms. Finally, these two are connected in series. No? Simply we have Rn, this is 6 by 5 plus 3. What is the value? That is 15 plus 6 by 5, that is 21 by 5, 21 by 5, which is equals to approximately 4.2, not approximately, it is equals to 4.2 ohm, that is Rn. Rn is 4.2 ohms. So, this is the value of equivalent resistance of this circuit, that is 4.2 ohms. Now, we have to obtain the equivalent circuit of Norton's, that is current source is parallel with that Norton's resistance, that is step 3. So, this is step 3, that is obtain Norton's equivalent circuit by connecting a current source in parallel with or Norton's resistance. So, what is the value of ISC? That is approximately 4 amps, no? 4 amps. Here Rn is what? 4.2, which is equals to 4.2 ohms. This is Norton's equivalent circuit. Next, what is step 4? Reconnect the load resistance across these two terminals and calculate the load current. The same step can be applicable here. This is step 4. Reconnect 4 ohm branch and calculate load current, means this current IL. Okay, we have Norton's current, we have Norton's resistance, we have the removed load resistance. So, finally, we have connected this load resistance across these two terminals and we have to calculate the Norton's current. So, what is the value of Norton's current here? The current through this branch we have to calculate, means what? We have to apply, that is load current equals to total current in the circuit, that is IN, which is multiplied by, we have to calculate the current through this branch, no? We have to apply current division principle. So, total current in the circuit, which is multiplied by opposite branch resistance by total resistance, that is opposite branch resistance is nothing but Rn by total resistance Rn plus RL. So, like this we have to calculate what is the value of IN, here it is 4 into what is the value of Rn, 4.2 by 4.2 plus 4, 8.2, approximately 4 by 8, that is 1 by 2, approximately 4 into 1 by 2, which is equals to 2 amps. The load current is approximately IL is equals to 2 amps, approximately it is 2 amps, which is equals to 2 amps. So, like this we have to calculate the current through any branch. Simple. First, in case of step 1, we have to remove the load resistance and short circuit those two terminals and calculate the short circuit current. In case of step 2, remove the load terminals and deactivate the current sources with their internal resistances and calculate the equivalent resistance. That resistance is nothing but Norton's resistance. And then step 3, reconnect, means we have to obtain the Norton's equivalent circuit by connecting obtain short circuit current and Norton's resistance, which are connected in parallel. In step 4, we have to reconnect the removed low resistance across these two terminals and calculate the current through that branch. That current is nothing but load current. This is the formula to get that load current. Okay. Like this, we have to solve the problem by using Norton's theorem. Now, we have important observation, that is, this is the equivalent circuit of Thevenin's theorem, and this is the equivalent circuit of Norton's theorem. There we have to connect the Thevenin's voltage in series with the Thevenin's resistance. Here we have to connect the Norton's current in parallel with the Norton's resistance. So, these are mutually transferable, means what? We have to apply source transformation principle. So, series connected voltage source with the resistance is converted to parallelly connected IN and RN. So, in case of source transformation principle, the voltage source can be converted to current source like this, no. So, from this we have VTH and RTH, here we have IN and RN. Okay. So, here VTH value is nothing but what? Like this you have to write Rn. So, for example, if we have the Norton's current IN into RTH, which is equals to Rn. RTH is always Rn, because what is step 2? Replace all internal replace voltage sources with their internal resistances and calculate the equivalent resistance. The same step 2 can be applicable in case of Norton's theorem also. So, there is no change in the value of resistance in both the cases. So, that is why RTH is equals to Rn. RTH is equals to Rn. In this case, what is the value of Norton's current? That is VTH by RTH or Rn. So, this is the very important observation. For example, if you have VTH 10 volts and ISC, for example, 2 amps, then what is the value of Rn he wants to calculate? Means what? In case of Norton's theorem, the Norton's resistance, or in case of Thevenin's theorem, the Thevenin's resistance, both are equal, which is equals to what? RTH only, no? That is RTH, which is equals to Rn, which is equals to VTH by ISC. So, what is the value of V? Which is equals to 2, which is equals to 5 ohms. So, the value of RTH is nothing but 5 ohms. So, like this we have to calculate the required value of that given data.